Okay, good. So next we'd get negative 105 and 2. And those would add to,
Negative 103.
okay? Keep going. What about 3? Does 3 go into 210? It does. How do you know that it does, by the way?
Because it's negative 21 times 10.
Okay, but there's another way too.
If you add all the numbers and the value of the digit and it equals to a multiple of 3, then we can divide by
Very good, very good. If you add up all of the digits in a number, and it doesn't matter how spectacularly big the number is, if you add up all the digits and the result is divisible by 3, and you could even go one step further than that. You could even say, like, we'll come back to that in a second. If I had some just ridiculous number, like let's say we had 9, 5, 4, 7, 2, 3, 0, 6, 5, 1. Okay, get some really big number. Is it divisible by 3? If I add all those up, what do I get? 9 plus 5 is, actually 9 plus 9 is 18, and 2 is 20, plus 10 is 30, plus 41, 42?
Yeah.
Okay, so that equals, if I add them up, I get 42. Is 42 divisible by 3? Well, I can add up that number again. I can keep doing this over and over again. 4 plus 2 is 6, and obviously 6 is divisible by 3. Okay? We probably knew 42 was divisible by 3, but you get that? You get the idea? Okay. So keep going. So we get now, this is going to be a 3. What's this going to be? On this side. So those add to 7. Okay, does 4 go into 210?
No.
No. Does 5?
Yeah.
Yeah. So 5 times 40, negative 42. So those add to, okay. Does 6 go into 210?
Yes.
Yeah, it does. You're right, it does. Okay. 6 times what? Negative 35?
Yeah.
We can tell from here, can't we? How?
Oh.
You see the pattern? Because if this one's going to double, then this one's going to get cut in half, and that one's even. So it's divisible by 2. Everybody see that? Kind of tricky. 7 go into 210?
Yes.
It does. Oh, by the way, what's that add to?
189.
7 times what? Negative 30? So negative 23. That's a lot. 8 does not, right? 9 does not, right? 10 does. 11 does not, right? Okay. 12. No, 12 does not, does it? No. 13? No, I know it's getting hard, isn't it? 13 does not. 14?
Yeah.
14 does. It does. 14 times what?
15.
Times 15. Okay. So now,
There's our
there's our number. But I want you to know, and this adds to negative 1. Now, we're not going to do this. But if I were to just kind of keep going with this, do you see what's going to happen? This is going to become a negative 14, and that becomes a positive 15. That, right? So there's 1. Then we'd go up to positive, this would become a negative 10, and this would become a positive 21, and we'd get positive 11, etc., right? And we get all the same numbers, but just opposite signs. I want you to tell me what if you notice any kind of a pattern here relating the factors that we chose and their sums. And this is really kind of an important thing in math. It's subtle, but you will take advantage of this later in math. Let me rephrase that. when does the sum of the factors get smallest? Okay, when the absolute values of the numbers are closer together, right? Does that make sense? So when the two factors were, the absolute value of one was 15, the absolute value of the other was 14, when they're about the same size is another way of saying that. That's when the sums get smaller. The sums get huge when the numbers are really disparate, when there's one is really big and one is really small. Make sense? Okay? So then how's that helpful? Well, if you're trying to find the numbers that multiply to negative 210 and add to negative 1, where are you going to start? You're going to start with the really extreme ones? No, you're going to try to find numbers that are very close together, right? Make sense? Okay, so that was a lot of work, but you see that that can really cut down your time when you're trying to to factor these enormous next year especially. We're going to have some really nasty ones next year. We know that our factors here then were negative 15, positive 14, right? So now back to bottoms up here. Where does that take us? We'll go this way.
X minus 15
X minus an X.
plus 14.
Okay, so we're going to write out x minus 15, x plus 14, and divide the whole thing. We'll divide the constants by 6. And now what?
Simplify.
Simplify. 15 over 6 reduces to 5 over 2, is that right? 5. So this one becomes x minus 5 halves. This one becomes 14 over 6,
7 over 3.
7 over 3, good. And one last step. Good. We're going to clear the fractions. We're going to have to multiply each expression through by the constant that will clear the fraction. So in the first case, we'll multiply by 2. Second case, we multiply by 3. What that amounts to, though, isn't it? When I multiply this one by 2, I'm just going to get a 2 out in front of the x minus 5. So really, in terms of a pattern, all you're doing is just moving that 2 up there, aren't you? Okay. So what's the other factor going to be then? Okay, that's it. Make sense? Everybody see that? Okay, so that's our brief review of factor. Okay, what I want to do, how much time have we got? These are such short periods of day. 6. We got a little time. 1:30. I've got 1:36 for 5th period, so we got a little time. All right, so what I want to do today, I want to just start reviewing how to simplify radicals. And we're going to focus exclusively on square roots for now. Later in the year, we might come back and add some other kinds of roots in there too. But if we want to simplify something like, let's say, start easy, say the square root of 20. What's the answer, first of all?
Something in
2
4 and 5.
square root
Say it again.
2 square root 5.
2 square root of 5 is correct. How do we get there? And I bet you a lot of you can just tell me what the answer is. But it's really important that we think of this in terms of a process, because that same process we're going to apply later to much harder kinds of radicals. So how did we get there? What did we do to that 20 that allowed us to somehow extricate the 2 from the radical? Okay, so we're going to find factors of 20, and in specifically what we're looking for here. If we can simplify a radical, this one simplifies, but for example, this one does not, right? Okay, they both have factors. Somebody give me an example of what are some factors of 15? 3 and 5. So I can factor it, but those factors worked, or didn't work, and somehow we had factors here that did work. What was the difference?
4 and 5, 4
Okay, what about the 4?
It has factors of perfect squares.
Okay, it has a perfect square factor. We're looking for the biggest perfect square factor of 20. 20, we can break the 20 up into a 4 times 5, right? And here's a property of radicals. If I have the square root of a product of A times B, for example, I can always split that up into separate radicals. So I can break that up into the square root of A times the square root of B. That's always true. So all I'm really going to do here is I'm just going to write this as square root of 4 times square root of 5. And what is the square root of 4? 2. Now, I would say that really you can skip this step. I think it's perfectly fine just to skip down to there. Just combine those two steps. It didn't work out so well over here, though, because neither of those factors was a perfect square, and so it didn't help us, right? Okay, what about, let's try another one, though. What about something like this? Okay, try that on your own real quick. Okay, what's the verdict? What's the biggest perfect square that divides into 48? 16. Okay, now, so we can do this pretty easily in one step if we get that. But what if we miss that? What if we just, what's another perfect square? 4. So what if we thought, oh, well, 4. Okay, so could we still get to the answer? Yeah, we could. If I wrote this as, oops. If I wrote this as the square root of 4 times the square root of 12, that would just give me 2 times the square root of 12. But I always have to check and say, okay, did I get it? Is there a perfect square that divides into 12? Yeah, 4 does, right? So I can split this into 2 times the square root of 4 times the square root of 3, right? Square root of 4 is 2, times 2 is 4, right? Okay, no biggie. Okay, what happens if I throw something like this at you then? What if we've got, say, stare at that. Don't say anything. Stare at that for a second. Right? You can work on your note paper if you want to, but just see if you come up with a strategy for this. There are many ways to do this, but see if we come up with maybe the best way, easiest way. Okay, what do we think? Any suggestions? And I'm not looking, right now, I don't care, I just want a way. It doesn't have to end up being the way that we all decide was the easiest. What's a way to do this, Duncan? What do you think?
Multiply 15 with 10.
Yeah, sure, we could. We could just write this as the square root of 150. And in this case, that's helpful probably because we know what's a perfect square factor of 150. 25, right? So we could write this as the square root of 25 times the square root of 6. So what's our answer?
5 squared is 6.
Good. Okay, I think that's fine. Now, sometimes, what's the potential disadvantage of that strategy in general? Say it again? The numbers get big, right? We got a 150 here, which worked out fine, but what if that had been something different, like a 182 or something? You know, they start to get a little bit cumbersome, right? Any other ideas? What do you think?
You factor the 2 numbers in.
Okay, yeah. Let's factor each of the 2 individual numbers, even though, are there any perfect square factors of 15? No. Any perfect square factors of 10? No, but if one of those non-perfect square factors shows up twice, what is something times itself equal to? That's a square, right? So if we break this up, this 15, we can break that up into the square root of 5 times the square root of 3. The square root of 10 we break up into square root of 5 times square root of 2. Well, what do you notice? Look at this. I've got a square root of 5 squared. A square root of 5 times the square root of 5 is, well, 5, right? Square root of 25, which is just 5. If you multiply a square root times itself, that's effectively squaring, and it just undoes the radical, right? So this becomes a 5. That's not very 5. And then, so those are taken care of. We're left with the square root of 3 times the square root of 2. We can't do anything with that, can we? So we're left with 5 times square root of 6. Make sense?
So you just multiply them?
Say it again.
So you just multiply the two left over?
Right, because I couldn't do anything with those. The 3 and the 2, none of those showed up more than once, right? So we're stuck with that 6. Okay, last issue, and then we're really done with this. What if you have something like, let's say, the square root of 7 over 2? Okay, do you remember this nonsense? And I say nonsense because this is kind of, in a way, I think, this is, everybody real quick, who's got a calculator handy? Okay, somebody, take, what is the square root of 7 halves? 1.87, blah, blah, blah. You get some decimal, right? But you get an answer. There's nothing wrong with the square root of 7 halves. It really is a number. But in math, a lot of times we don't like to have irrational numbers in the denominator. We like the denominators to be rationalized. And so, do you remember dealing with this stuff last year?
No, we didn't do this last year.
You didn't do this last year, okay. So let's talk about this. So what do we have to do? We've got to get rid of that square root in the bottom. So the first thing we do, just like we were able to say that the square root of a product is equal to the product of the square roots, we can split it up into a product of 2 square roots. What do you think we can do with the quotient?
You can split it up.
Split it up. Okay, we can also say
So it'd be 7 divided by the square, so it'd be the square root of 7 divided by the square root of 2.
square root of 7 divided by the square root of 2, exactly. We can always say this, the square root of a quotient equals the separate square roots, or the fraction of the separate square roots, the quotient. So we can rewrite this as the square root of 7 by the square root of 2. Are either of those, can we reduce either of those radicals, simplify them? Not by themselves, we can't. So you'd be tempted to say we're done, but the problem is we can't have that square root on the bottom. That's a no-no. Any suggestions?
Times it by the square root of 2.
But say it again.
Times it by the square root of 2.
Almost. I think you're getting at the right thing. We gotta be careful how we say this. In math, what are the only ways that we can preserve the identity of a number? We can if I want to preserve the identity, I can multiply by, no, what's identity mean?
Both sides.
We're getting there, The identity is just the value of something, right? If I want to preserve the identity of a number, I'm going to multiply by what, have you ever talked about the multiplicative identity before? Long time ago, probably? The maybe we better spend just a second on this. This is very important. Okay.
I wish I did. You wish you loved.
Yep.
New wall this.
Oh,
New wall.
Okay, there's a little fine print here. What I'm talking about now, this is only applies to real numbers. Does not apply to imaginary numbers, nor does it apply to matrices or other things that we'll eventually talk about this year and or next year. So this is just for real numbers, the identity numbers. The multiplicative identity, and that's kind of a mouthful, but I think probably the better way to say it is just the identity number for multiplication would be just as good. That is equal to what? Let me know. In other words,
Absolute value.
not absolute value. I think this will help. In other words, this, if I've got some number where A is just a real number, A times what equals A, so the identity is unchanged? 1. So 1 is the special number for multiplication. It's the identity number for multiplication, or the multiplicative identity. I can multiply anything by 1 and keep it the same, in other words. Right? Does that make sense? That thing, yeah. Okay, what about the additive identity? Ah, okay. Because any number plus what number equals itself, well, that's 0, right? Okay, why is that important? It's important because in situations like this, am I trying to change the value of my answer? In other words, when I'm all done, if I put the answer in my calculator, don't I still need to get back that same decimal, right? So all I can do is add 0 or multiply by 1. Multiplying by 1 is almost always what we end up doing. What would it look like here? Say it again.
Multiply the bottom by 1.
I'm gonna multiply the whole thing by 1. So I'm gonna multiply this whole fraction by something divided by something. But any fraction that has the same thing on the top and the bottom equals 1, doesn't it?
Yeah.
Which part of this fraction is determining, which part do I have to change? The bottom. So what would I need to multiply the bottom by to eliminate the radical? The square root of 2 times what would become a non-square root?
Square root.
Square root of 2. Why not? Square root of 2 times square root of 2 is what? 2, right? So I need to multiply the bottom by the square root of 2 so that I can get an answer on the bottom of 2, right? Instead of square root of 2. But if I multiply the bottom by that, what do I have to multiply the top by? Square root of 2, because I can only multiply by 1. You see? Okay, so on the top, what do I end up with? The square root of 7 times the square root of 2 is square root of 14. Yeah. Okay, and that's my answer. Why is that better? Well, I don't know that it is. It's better to mathematicians because the bottom is rationalized. It's not a square root. Okay. All right, let's try a couple of these. This is probably the hardest thing to do, so let's practice this the most. How about this one? Simplify this for me. What do we get? Any ideas? Okay, somebody say it again. Square root of 12. Okay, and the way we got to that is how? You multiplied by square root of 4 over square root of 4. Okay, everybody do that? Okay, that works. But we're going to have to simplify that answer. Is there maybe, what do you think, different way? What? Square root of 5 over 2? Yeah, how come? This one, I tricked you. This one was an easy one. You didn't really have to do anything here, did you? Because we can split this up into the square root of 5 over the square root of 4. And what's the square root of 4? It's just plain old 2, right? So, and we're done. We didn't have to go any further because the bottom was an integer, right? It wasn't a square root. Okay? Another one. Oh, probably not gonna have time. Let's see. wrote that the wrong way. I wanted to write it like this. Well, what did I have on top? 8, yeah. Any suggestions on this one? What do you think? Help me.
Simplify the fraction.
Yeah. Simplify the fraction first, right? That might make it a lot easier. What's a number that goes into both of those?
8.
Does 8, not 8, but 2 does, right? So I could rewrite this as what? The square root of 4 over 27? That's a little better, right? What's the next step? Good. Square root of 4 over square root of 27. Square root of 4 simplifies, right? Okay, now what about this guy? Square root of 27. Can we simplify that? Because if we can, it'd sure be nice. That's a big number. Okay, I get it. Oh. Well, we'll finish this example up and go to the lab tomorrow.
So you're pushing those.
Yep, I'll push him back. Yep.
I would judge